I'd like you to compute the line integral over some path C of yi minus xj dot dr, and I'd like the path to be the unit circle traversed clockwise, just its upper half, and then the return line segment that is along the x-axis. Before watching any more of the video, go ahead and start working on this problem, and I'll start by parameterizing the path. So if you'd like to check your parameterization by going on once you finish that, press play again. One type of parameterization is clearly not going to deal with this half circle and with this straight line, so we're going to have to do the parameterization in two parts. We'll start with the half circle parameterization. Along this path, x is going from -1 up to 1, and y is going from 0 up to 1, and then back down to 0. And we're going to use trigonometric functions because it's a circle, so we need to find a trigonometric function that's going from -1 to 1 over the time interval we choose, and a different one that goes from 0 to 1 and then back from 1 to 0. We choose x of t is negative cosine t and start with t equals 0. So at time 0, cosine is 1, so this gives us -1. And we go to time pi, at which point cosine is -1, so this gives us 1. So that's great for x. It's going from -1 to 1. And then for y, we choose sine of t, and that is 0 at 0, and it's 0 again at pi. And in between, at pi over 2, it will hit 1. So these functions are a parameterization of the upper curve. Written in our vector notation, our position vector r of t is negative cosine of ti plus sine of tj for this range of t. And now we need to deal with the bottom line. We're going to just do it completely separately. So we're not going to make time continue. We're going to use the fact that the line integral around the whole thing is equal to the line integral around the upper plus the line integral around the bottom, and we're just going to create a completely separate parameterization along the bottom for computing that line integral separately. Mathematically, the line integral over the whole path is equal to the line integral over this upper piece of the path plus the line integral over this lower piece of the path. To parameterize this line, y is 0 the whole time on that line, and x is going from 1 to -1, so I guess we could use cosine actually again because we know it goes from 1 to -1 as t goes from 0 to pi. Or we could use a linear function of time, so we could start at 1 at time 0 and move linearly at a rate of, I don't know, -1 or something. So this would be 1 minus t, and we would choose a range of t so that we land at -1. So I'm going to go ahead and do that. Okay, so I said we want 1 at time 0, and we want this to be a linear function of time. So 1 minus t, and if we plug in 0, we get 1. And then whatever our final time is, we need to be at x equals -1. So 1 minus t is equal to -1 at our final time. So that's actually t final. So t final is equal to 2. And so x of t is 1 minus t for t in between 0 and 2. And y of t is just always 0. And back in our vector notation, r of t is equal to 1 minus ti. So we finished parameterizing our paths. We're ready to start setting up the line integral. Here are the two paths, negative cosine ti plus sine tj, and 1 minus ti. This is our upper half circle, and this is our return along the axis. And so now we're going to find the velocity vectors that give us little direction pieces along these curves. So we find these little velocity vectors, dr1 dt, and they are the derivative of cosine is negative sine, but we have this negative sign, so sine ti plus cosine tj. And the derivative of our second path is -1i. So now we have both of our velocity vectors. So those little vectors along the second path look like this. We recall that to compute the line integral, we pick a particular path, and on that path, on the path x is x of t for the path, and y is y of t for the path, and we use for dr our vectors dr dt. So we're going to plug in the information from r1 and r2 to set up two of these integrals. I didn't have a ton of space, so sorry about this formatting. So this line integral over that upper half curve, y was sine of t, negative x was the negative of negative cosine t. So this is what our vector field is along the path. If I choose a point on this path right there at time something and ask for what the vector field looks like, it's given by this expression. And then these are the velocity vectors that are along the path. And it turns out that actually the vector field and the velocity vectors are identical, so we should get a large positive line integral from this. And so I have the dot product of this vector field with what the path is doing, and I'm just going to compute that out. Thanks to my favorite trig identity, this works out super nicely, and we just get pi. And so now we need to add to this whatever was happening along the bottom. So here we plug in our y value, which was 0, so we have 0i, and we subtract our x value times j, so negative 1 minus tj. That's based on what our vector field was, and it was given to us. And then our velocity vectors were negative 1i. But when we look at this, we have a 0i here and a negative 1i here, so that's going to dot to 0. And we have something about t here, but we have a 0 here, that's going to dot to 0. This is equal to the integral from 0 to 2 of 0 dt equals 0. So total is pi plus 0 equals pi. Let's look a little more into this, though, because probably we didn't even need to bother to parameterize the path. This is like so clearly a 0 that let's see if we could have thought about the vector field and the path and skipped the work of doing the parameterization. So our path was along the x-axis going backwards, and let's draw in some of our vectors there. Okay, so y equals 0 there, so f is negative xj on x-axis. Negative xj, so we're over here, and that gives us pointing downward, pointing further downward, pointing upward, pointing further upward. Okay, it's obvious just by looking that the vector field has only a j component along the axis, and the path obviously has no j component, and so no matter how we parameterize this path, the dot product between what the vector field is doing and the direction of motion along the path is definitely 0. So f dot delta r equals 0 on x-axis. So we definitely could have skipped the work of parameterizing that path and setting up the line integral. We could have just made this straightforward argument based on the picture that would have had a 0 contribution and that we only had to worry about this upper part. Okay, cool.